by now you've had some experience using the small electron microscope, the TM1000. Now we're going to add some theory behind what's actually happening inside the electron microscope. And I actually delayed this until now, until you had a chance to use the small electron microscope, because hopefully it'll help it make a little bit more sense to you. So here's a cutaway of what the inside of our electron microscopes look like. This is not exactly ours, but it's going to be very similar inside. Essentially what we have is we have an electron gun up here, which we're going to induce to send a beam of electrons down to our specimen down here in the chamber. And to focus that specimen, we'll be using a series of electromagnets. Now we can't use glass lenses like you find on a regular microscope because the electron beam won't go through glass. But the electrons have a charge, which means that they're influenced by magnetic fields. So these rings right here, these condenser lenses, if you will, are actually just electromagnets. And the idea is to get those electrons finally focused right down here on the sample. So first of all, let's take a look at the electron gun. Electron gun, here's a photograph taken with the Leica dissecting microscope. This is called a thermionic electron gun, which basically means we're going to heat it up. It's going to give off a bunch of electrons. To give you some idea of the scale here, this is just a penny I had in my pocket. I stuck down there with it so you could see what's going on. By the way, just to show you a nice image from the Leica here, you can see that this filament's actually burned out. So this wears away as we use it. We put that 15,000 volts through there, or on the big scope we'll put up to 30,000 volts through this filament, and it eventually burns away. Alright, so let's go back and look at our cutaway again. So the way we get these electrons to head down toward the specimen is the fact that under this you'll see a disc called an anode. And anodes have a positive charge, and of course negatively charged electrons are going to be attracted to our positively charged anode, so they head off in that direction. But there's a hole right in the middle of the anode, so once these guys start moving toward the anode, some of them will simply go right through it. Also, the stage down here on which you're going to mount your specimen also has a positive charge, so that also keeps the electrons moving in this direction. This can cause us a problem. A lot of things we look at in our microscopes are non-conductive. And as you found out with hopefully with the TM1000, if you have something that's non-conductive, it can actually gather a charge, and then it gives off lots of electrons, and all we see is a glow. So let's take a look at what happens when the electron beam hits the specimen and how that ends up making an image on our computer screen. So here you can see the electron beam heading down. It hits the specimen here, and then there's actually two types of electrons that are going to come off of this. In one case, we're going to get the what are known as secondary electrons, and that is when the electron beam comes down and hits the atoms of the specimen. Those atoms absorb the energy and give off their own electrons. There's a detector to pick up secondary electrons over here, as you can see, and that detector to attract those electrons has a positive charge on it. It's about 300 volts, which is actually quite a lot. And then once those electrons come in to the Faraday cage, which is positively charged, they hit the detector. And then the detector uses the information from those electrons to form the image on our computer screen. Now the second type of electrons are called backscatter electrons. And these electrons actually don't come from the atoms, they actually reflect off the surface. And they actually can come even from deeper down in the specimen. And we have a second detector that can actually detect those. So this is to show you, this illustration will actually show you where these electrons are going to come from. So you can see here the secondary electrons are going to be surface electrons. So they're very shallow, but these are very, very good for getting surface features. And of course, that's one of the main reasons for using a scanning electron microscope. The backscatter electrons are going to come from deeper in the specimen. So some will bounce right off the surface, some will go deeper. And then the ones that are really deep actually never get back out again. So when they get absorbed, they give off X-rays. Now we actually don't have an X-ray detector for our scope, but you can do elemental analysis by looking at X-rays. So the detectors that we have on our scope are the secondary electron detectors and the backscatter detectors. So why is it called a scanning electron microscope? Well, as you can see from this illustration, here's our primary beam coming down, and it's actually making the picture pixel by pixel. It's hitting from left to right, top to bottom, and every time it hits, we get electrons from that particular part of the specimen. Interestingly enough, if you want to magnify, all we do instead of actually scanning across a big image like this, so we just would scan over a smaller box. So this is actually showing the setup. As you can see here, we've got the column here, so all the electromagnets are up above there. The electrons come out through the pole piece here, they hit our specimen. The secondary electrons over here to the side, and then of course our backscatter detector is actually going to be up here mounted to the pole piece. And you saw a picture of that inside of the TM1000.